So, okay, let us start. We are now going to, we have seen in the morning the toric quotient presentation and the toric Cox ring. We have seen right after that in Emmanuel's talk the universal torso, and we go in this direction, but slightly change the direction, and we'll introduce Cox rings and Cox sheaves and characteristic spaces for a certain class of varieties. Still everything over the complex numbers in these talks. In this talk, what I want is X an irreducible normal variety, and not necessary for everything, but general assumption as for the whole section. I want that the divisor class group is finitely generated. This excludes some varieties. And I also want that that is maybe not such big restriction as this one is. I wanted the globally invertible functions, that they are all constant. That's for the next 90 minutes what we ask them to be. So on these varieties, they are normal. We have while divisors. We know about principal divisors. We have divisor class group for sure. And while divisors, they form a group with respect to addition, and I'm looking at a subgroup. Any subgroup for the moment. And well, maybe also here restrict to the finitely generated case. So not any, finitely generated subgroup of the while divisor group. Then I can associate sheaf of divisorial algebras. This will be a graded sheaf of graded algebras. And the grading goes via that group, and I take divisors from this K coming from this group, and there will be homogeneous components. And now I have to say, what is the homogeneous component? The homogeneous component is just the reflexive sheaf associated with this divisor. That means, what are the, if you have an open subset U, what are the elements of sections? These are rational functions with a property that on this open subset U, divisor of the function plus d is greater or equal to 0. Are you fine with that? Sounds good. Okay, these are the sheaf of divisorial algebra. So far it's maybe a sheaf, and I should say why it's a sheaf of algebras. Vector spaces is clear. Why algebras? Now we need a multiplication. So how to do this? I mean, we say what we want to do on homogeneous elements with respect to this grading. So take some rational function f over U, it has divisor such that the sum is bigger than 0 here, and maybe another function g living in another homogeneous component. And what can we say? Yeah, I mean, we are in the function field and we can take the product of these functions. And by the rule of divisors, we know that the divisor of the product is the sum of the divisors. So it fulfills the necessary inequality that we land in the sections over U of S d plus E. And that is what you need for a graded algebra. Now you can multiply any functions by developing into homogeneous and so on and so on. Okay, so we have these algebras. Now comes a proposition which we also saw already in Emmanuel's talk, but in other words. Question? No. If we take of course, finitely generated, that means somehow small, but big enough in the sense that it surjects onto the divisor class group. So take representatives for generators of the class group and you get a big group which is big enough in this sense but still finitely generated. Then the graded algebra of global sections of this sheaf of divisorial algebras is a unique factorization domain. That is basically the algebraic version, if we got you right, Emmanuel, of what you said. If we pull back everything with respect to the universal torsor, you make this divisor or bundle classes trivial. I'm not going to prove this. It takes a while. But we have this result. So that is a statement. And now, okay, we could be fine with divisorial algebras because we have this nice result, but they are not universal in some sense. Because what is the problem with this? The problem is that you could have divisors in your group which are linearly equivalent to each other. That is not a problem, but it means that in this concept we have redundancies. We are looking for something more universal. That means we have to get rid of the redundancies. And that is possible, and that is our next construction. So, we have finitely generated divisor class groups, and we can take any subgroup such that finitely generated such that the projection onto the class group is surjective, and we have to give the projection a name for this construction. Let us call it C. That means passing to the divisor class, this C. And that is exactly what we do. We take a divisor belonging to this group, and we map it to its class. And this has to be surjective. So maybe we have too many. Group K is too big. Can you say me a situation where it definitely must be too big? Where we never have a chance to make it. Where are the bad guys? Torsion. As soon as we have torsion in the class group, no chance, because if you have a finitely generated subgroup of a group of Weil divisors, it's a torsion-free group, it will always be torsion-free. But reality shows that there are lots of interesting varieties with torsion in the class group. They force us to do this. I mean, if we don't have torsion, then we can just take a basis of the class group, representatives above takes a K, and we have something which looks good. So what we do is, the idea is to identify isomorphic homogeneous components, but we have to do it, we want an algebra at the end, we have to do it in a systematic way. The first step of the systematic way is that we look at the kernel of the projection. It is K over 0. It is just the intersection of the group of principal divisors with our K. So the next thing is that I choose a kind of character on this K0, on this K0. And what this means? This means I choose a homomorphism. Write it by K. It should be a non-zero rational function on our X with a property that the divisor of this function is again D. So this goes from K0. I do two things. I takes it, function, chi of D, is a rational function, and you should give back as its divisor, the D. How the hell can we find such function? It is not so difficult. I mean, we have this finitely generated group K, we have the kernel. We know by elementary divisor theorem that there is a basis of the kernel. I don't even know, I just need a basis of the kernel. Then I have, say, if the kernel is somehow, the basis has K members, small k, how to define the remaining Ks just as products of the basis elements. And then the rules of divisor show me that this gives a homomorphism. That means it is compatible with addition of divisors. Choose a basis, start with Ki, and multiply them. Monomials in the Ki, and we are done. So this is doable. I feel that I violate the automatism here. I don't know how long I can do this without being somehow getting into trouble. Yeah. And now, so this should hold for all divisors here. So now the idea to identify components in a systematic way means we have a divisorial algebra, we want to get an algebra, what can we do? We have to mod out an ideal to get an algebra. So yeah, we defined already it's a direct sum. Or its homogeneous components. And here's the ideal. It will be generated by global sections. This will have good consequences for the factor algebra, as we will see soon. And what I'm doing, I want to get rid of the principal divisors and their components. So I will identify all those where this E runs through the kernel. And now I have to say, okay, chi I, this is a rational function. I have still to specify in which degree of my S it lives. Okay, what we always can do, we can put this guy into regarded as a global section of S minus E. So if I take the divisor of this chi of D and the degree, at the end it is an invertible element, and that is what we want to get rid of, homogeneous invertible elements. Okay, so then I do the factor sheaf. I can do that. Usually it's not much fun to build a factor sheaf. It means you have to pre-sheaf, sheafify something and so on and so on. I have a good news in a few minutes. Here it is. Super easy. And what we also consider is, if we have this, we have a projection homomorphism of the sheaves. Okay, so then, what can we do? So far we have a sheaf, but we want to have a graded sheaf. And we get a graded sheaf. And this graded sheaf, this sheaf will be graded by the divisor class group. What is a divisor class group? I mean, by our choice, a divisor class group is K mod K naught. This was surjective, and this was the kernel of the projection. So we get a grading by the divisor class group. In which way we have to coarsen the given grading, the K grading of the divisorial algebra S, in a manner that it survives the projection to the quotient. That's all we have to do. So what we do is just we take all SD prime, where D prime is of the same class as D and comes from K. So D prime is taken from C to the minus 1, all divisors, D prime which live in K, and project. So far, apart from big symbols, I think it is very natural and not too hard what we did. And this guy has a name. this is what I call the Cox sheaf. And the Cox ring. The Cox ring is just the ring of global sections. And of course, this is also graded. These are the goes over the divisor class group. And we take the homogeneous component here. Okay. So, two things. There are some questions about this construction. I did a lot of choices. Why I'm allowed to do this? Okay, I'm the one who gives the talk, so maybe that is. But this is a dangerous excuse. we will look for a more safe one, so that we. And another question is, we met already in the morning, and maybe this question is more interesting. I don't know, maybe less interesting, but for us it could be interesting. Note where I am. I have to use this blackboard. Yeah.
I might be confused, but from what you've written here, isn't the Cochrane?
You are completely right. What I want is to take the global sections. And yes. Thank you. You are completely right. So even 3 questions, and this was the most important one. Okay. It's not a question, but I claim something. We have seen the Cox ring for toric variety. No. We have seen this in the morning. It was constructed by some elementary process. So, this was before noon. And now we have again a Cox ring. That is the guy after noon, AM and PM. Why they are equal? Constructions are quite different. I leave you alone with this problem. Is that okay? The first step is to realize that there is a problem. The second step is to solve it. And the third step is to ask me if you can't solve it. Is this a good proposal to live with? Okay, so it is indeed the same. It is constructed, though it looks. Now, some facts about this. The Cox sheaf and the Cox ring, they don't depend on the choices made. Also, you have to go through the choices. It is an elementary, but proof with a couple of details. Let us believe it. Good news about the quotient sheaf. Something which you always want to do, but you are not allowed in general. You can, on the level of sections, you can stay with the pre-sheaf. If you build a quotient sheaf, first you take section-wise quotients. That's a pre-sheaf, but in general not a sheaf. In this case, yes. So, by the ideal. So other good news. We know about the homogeneous components. What are they? For each divisor from our group of K of divisors which we fixed at the beginning of the construction, we get a canonical isomorphism of, and for any open subset in the sections, the homogeneous sections of degree D. That means we are really in some OX of D and have some sections over some U, then that is isomorphic via the, where is the projection? Pi. Somewhere. Okay. If we take the projection, and that is the meaning of canonical in this context, then it is isomorphic to the class D homogeneous component of the Cox sheaf. That means component-wise, we still have what we want, namely just sections of reflexive sheaf, but in total, we had to do this in order we have to mod out something in order to get really redundance-free construction. And another news is if I have algebras and we are in algebraic geometry, the first question is, the good guys or the bad guys, is it good or bad? Which means if it is finally generated, then it's good in the sense that because we can classically associate an affine variety with it and so on and so on. So, when do we have this? What we can say, it's not a characterization, but it is at least a sufficient criterion if our x is q factorial. What does q factorial mean? Q factorial means that singularities are somehow mild in the sense that for any wild divisor I find some multiple which is in fact a line bundle or Cartier divisor. Yeah? So if you have such guy, then such variety, then we see that at least locally our Cox sheaf is finally generated. About the reverse direction, for sure, we know that that is not an equivalence. Why do we know this? once you have proven my claim, yeah, everything is finitely generated. And you have known Q factorial singularities. So it's not an equivalence. Questions to the birational geometers in the room. I don't know who wants the outcome to be a birational geometer. Nobody. I don't believe this. So you need not expose yourself in such a situation. But I don't know the answer. Maybe it's even known that I cannot say this. Can you characterize the singularities of my variety so that this sheaf is locally of finite type? I didn't seriously try, but it would be extremely interesting if there is a characterization of the singularities which allow that. So if you are eager and if you are a little bit birational geometer, why not check?
You want a one-to-one?
I don't know how this description of singularities could look like. So that you have a variety and finally generated class group, everything, and I want to know, can you tell me if the space has singularities of type blah blah blah, then it's locally finally generated. Sufficient criteria would be good, and equivalence would even be perfect.
Yeah,
is it?
Yeah, it is. Because though, I mean, you can do the same thing that they do for like ECHM. So I'm probably quoting myself as a variational geometer now.
Okay, you're allowed to do this.
Yeah, like, I mean, you can do the same thing that ECHM do when they prove the Fano varieties or Fano type varieties, weak Fano, whatever you want.
Yeah.
Finitely generated Cox-string, you can do the same thing locally for KLT singularities.
So you think that KLT could be or is?
Yeah, it is.
Did you write this somewhere?
Yes, in the paper with
So I just say are you fine with this? Because we are filmed, and tomorrow it will be. You will see this in the press and so on. But anyway, you can always say that I was the guy who.
Yeah, but there is one more step that goes into it, because if you do it this way, then you only get that, like, you have a local version of the Cox-string which is finitely generated over the local ring of the singularity.
Yeah.
All of these stalks are finitely generated, and then you have to prove that your version of local finite generation is the same as all stalks being finitely generated. And this is also true, but it's not like immediate.
So that's a little relief for me, so that I even at least posed a non-trivial question. But also, this is written somewhere?
Yeah, it's also the same thing.
Perfect. Okay, so thanks to Lucas. Oh, that would cause some noise. Okay, so now that we have the Cox ring, I'm going to present some collection of properties of this. Although they have to be proven, the proofs are sometimes a bit longer, so we want to get an overview over the properties. So for all non-empty open subsets U of our X, this ring, section ring of the Cox sheaf, in particular this will hold for the Cox ring itself, is an integral ring and it is normal ring. I mean, I don't know what is going to happen tomorrow with the torsors, but maybe this is a point to say where from at least what we don't do is go to complicated fields, which makes the situation much deeper, much more elaborate than in our setting. But what are we doing? We have a space with singularities, and we don't throw them away. We want to use the Cox ring machinery to say also something about the singularities. But if they are normal, this set of singularities is small. I can remove it without any effect on the sheaf of divisorial algebras. Because this sheaf is not blind, but a bit blind, it sees only up to codimension 2. And then we are in the setting of a smooth variety, and we are very close to the universal torsor setting.
Actually, it's exactly the same. This approach is equivalent to the one
it should be. It should.
Because you take a point which is outside of the support of this divisor.
Yeah, you anticipate my next remark.
Sorry.
But you can.
Both approaches coincide.
They coincide, but they look a bit.
Work to do for this.
What one can do is, don't take. If you don't want to choose finitely generated subgroup, if you want to go in a bit more, I mean, you have to make a choice at the end. I think what you can do, you can take a smooth point, and then you take all these function evaluating to 1 at this smooth point. Then you get a possibly infinitely non-finally generated subgroup. Okay, but you can do the same construction, and I think in this setting we should be quite close to the universal torsor construction.
Yes,
even
they can be identified.
Yeah.
A little bit of work because
okay.
done by this view time ago.
Okay, so
Maybe,
so that means
tomorrow.
we are going to learn about that. Very good.
Please state the construction.
Yeah. Now, geometry. Geometry. We also saw this already in some form in Emmanuel's talk. What I want to do is I take these sections of the Cox ring, or Cox sheaf if you want to, and I want to associate with them a divisor downstairs on my X. And this goes in the following, is the following definition. I can do this with homogeneous so the global, I do it globally. The D divisor notation. No, it's okay. The D divisor of this section is. I define it as the divisor of some f tilde plus another divisor. What are these? I'm going to specify in a second when I have free blackboard. The outcome of this D divisor, it will be an honest while divisor on X, and it will be an effective divisor. So let us be happy for the moment with that part of the blackboard. What is this D tilde? I can, yes. up to the top. But this was not my fault. It was by the device. It didn't stop. So we choose some other divisor, d tilde. Where this come from? It should come from our. I formulate this in terms of the construction. So K is a group from the construction we started with, finally generated subgroup, sheaf of divisorial algebras, factor algebra, and so on. And what I want is it should be of the same class. And what I took also a function f tilde. F tilde is in the global sections of S d tilde. And what we want to have is that this canonical isomorphism, which identifies this homogeneous component with the one in the Cox ring, and that means pi of f tilde should be equal to our f. There's a unique I, and again you have to show that it doesn't depend on all the choices made in this construction, but the point is if you compare another f tilde with the old f tilde, the difference is exactly in our ideal which we mod out. After all, we see this directly. So it is also not dependent on the choices. And now we can play a lot with this D divisor. Delocalization of X at a non-zero homogeneous element of the Cox ring. What should this be? I mean, the name, it must have a name. We need D, we need this F, and what we do is we have to, I mean, what is geometric localization? In the affine case, you move out divisor of a function, support of the divisor of a function. Okay, that's what we are doing here as well. Okay, so looks familiar. The only one difference is that this function D doesn't live on our X. It lives somewhere in the Cox ring. Proposition. Why is it nice to have this? All assumptions as before. If I want to know the sections of the Cox sheaf on such delocalization, then this is take the Cox ring and localize it by the element f. That is a very common formula which you see in the beginning of algebraic geometry lecture in whatever setting. Okay, a corollary of this immediate corollary, which gives us more finitely generated Cox rings, or locally finitely generated, more locally, examples of locally finite generated Cox sheaves. Once we know that the Cox ring is finitely generated, then we can localize and see that the Cox sheaf must also be locally of finite type. That means we see that in the toric case where the Cox ring is finally generated, the Cox sheaf locally is also of finite type. Now, for something completely different. This is just to check your age. Somebody knows that. Yeah. I don't know if I'm able to produce as much high quality fun. If we have a finitely generated abelian group, and a graded algebra, any finitely generated or not, the only thing we want to have is that it is integral. What we want to do is divisibility properties of graded algebras. Divisibility properties in general, it's okay what we have to do. For graded algebras, we can also take the old one, but we can also say something which is a little bit weaker if we try to formulate all divisibility theory only in the monoid of homogeneous elements. That is what we are going to do now. I say that if I have an element in this algebra which is non-zero, and it should not be a unit, so take a non-zero, a non-unit. I call this not prime but k prime. And you can guess what is first. It should be homogeneous. And second, if f divides a product not of any gh, but homogeneous gh, then it has to divide one of the factors at least. So I took a definition of prime element and just restrict this somehow to the homogeneous case. Ha! That is good. You didn't know about this. The second definition is... Sorry?
Like this definition, where is k involved?
G well, so let me try to reconstruct what I told you. So we take a function which is non-zero, non-unit. I call this guy k prime, and if it is homogeneous and So it must, the F should be homogeneous, and we must have this conclusion. Whenever F divides a product of two homogeneous guys, then it has to divide one of the factors. I think the logical part was missing from this. Sorry. Thank you. Are you okay with it now? Thank you. And now we define the homogeneous version of a unique factorization domain. Yeah, okay. If each homogeneous non-zero non-unit is a product of k primes. One can state this, one can ask oneself, what does it mean? An example. What does it have to do with classical UFT? Are there cases when this is the same as classical? Are there maybe more of this type? I put my condition on less functions, so it could be weaker, and it is weaker. Let us look at this ring. And now what we need, what I can tell you that if we have a torsion-free grading group, then we are not away from classical factoriality. But if we have torsion, so then new life pops up. So then so I'm taking a very prominent grading group, and how is the grading? I have to say what are the degrees of, I'm going to put a grading on the factor algebra, so what are the degrees of the generators? So that is the grading, and what I claim is, no, here I can do by hand. What I claim is, if we do it like that, this is not a UFT. And it is at least k factorial. So now I need a volunteer, not to solve the problem, but somebody who knows maybe already the solution, why all these holes, and can support me with. My plan is to explain this, and if there is a volunteer and wiping the blackboard, the other blackboards, I see you are not so. Oh wow, you're willing to do that?
What?
I'm extremely grateful.
You want me to squeegee or?
I'm even so grateful that no further requirements from my side.
Then I'll just erase.
Thank you so much. So, first question. Why it's not a UFT? You know. Does somebody know who came here without toric geometry? And now says, I know already why this is not. I tell you why you know. Because look at this. This, by a small trick, can be transformed, coordinate transformation in T1, T2, plus T squared. So you have a binomial. Solution set is a toric variety. You can compute convergency cone. You can go, yes, only the example. No, we are, everything is absolutely perfect. Only this example has to. That's the only, that is a natural reserve. Okay, so then we take divisor class group of this affine toric variety, and we will see that it is torsion Z mod 2Z. So it cannot be factorial.
But even so, T1, T2 is equal to T squared. Is another factorization.
Why it is K factorial? Next question. You can go into this geometry, but what happens? There is a good thing if you want to test factoriality is Nagata theorem on factoriality. If you have some ring, you have prime elements, and if you localize by the product of them, and what localization is homogeneous, and localization is factorial, then the original thing was as well. And we have a graded version of this Nagata theorem. What you have to do, you have to take k primes, you localize by them, and then go to the degree 0 part. If the degree 0 part is homogeneous, is factorial, then the whole ring is. So let us do this. What happens here? 0 set are 2 prime divisors. Look at the grading. What happens is the group interchanges the irreducible components. That means a divisor is k prime in a sense, and you can imagine that this means that the element is k prime. So now we are going to localize by the 3 variables, and the outcome, degree 0, we will see on Wednesday morning, is something very nice. It is part of an affine space. So it is something. And now I wonder if there are some real experts with a lot of knowing examples. This surface, it's a surface. When the toric one was even singular, we mod something out, still singular. What kind of singularity do we find downstairs? It should not be a toric singularity. You see it? We can see. I hope that if I'm not talking too much about other things, we will see on Wednesday how to treat surface singularities, C-star surface singularities, and we can determine the resolution. And at the end of this guy, what is the outcome? This here should be. Lucas, correct me if I'm telling nonsense. We are in the derived series of surface singularities. It is A1 over D4. Yeah? Okay. So this guy has A1, and the other guy is a D4 singularity, which is a non-toric singularity, because toric surface singularities, they are cyclic quotient, and this is more wild. It's by a non-abelian group. Okay. Thank you so much. Now, let us go back to Cox ring theory. I write the X is irreducible normal. We want a divisor class group to be finitely generated. We want the global invertible sections to be all constant. Then the Cox ring is CLX. Factorial. And if you know that the class group is torsion free, if it is torsion free, then it is then the Cox ring is even a unique factorization domain. Again, we know already why. So this is these properties are not equivalent. Counterexamples, look at toric geometry. Whenever the formula for the divisor class group, whenever our matrix P is for full rank but not lattice surjective, we have torsion in the class group. But the Cox ring is SUFD as you can ever want. That's a polynomial ring. Yes?
Is it in general that K factorial implies UFD for torsion-free K?
K factorial implies?
UFD for torsion-free K?
You mean in the context of rings? I wouldn't say no. But don't ask me 5 days later. Is that okay? Maybe you have to adjust a little bit. Maybe I can go more generally. I think so, and I even know where to look, but it is so long time ago.
Does K factorial in any sense give us a unique factorization?
Yes. For the homogeneous. I mean, how do we prove this? We use a D divisor. And if you have two homogeneous sections, and I want to know if one divides the other, then I look to the D divisors, and we get this beautiful relation as in formal life. We get the F divides G if and only if the D divisor of F is less equal to the E divisor of G. So divisibilities in terms of these divisors. And the next thing is an element, a homogeneous element, is K prime if and only if its divisor is a prime divisor. What are we doing? The D divisor downstairs, F is in the Cox ring. So what we have, so we reduce the divisibility discussion completely to looking at divisors downstairs. And what you have in the monoid of effective divisors is additive divisibility theory, and that's it. You can write every effective divisor as a positive, non-negative linear combination of prime divisors. And retranslate and you have it. So it is not as big as it sounds. So, we are going to associate a geometric object to the Cox sheaf. Finally generated divisor class group, we want to have all invertible global functions to be constant. And we suppose as I learned, that our X has KLT singularities. What I mean, locally of finite type. Cox sheaf is locally of finite type. What is easy to see, I told you, is if we are Q factorial or if we have finitely generated Cox ring, global Cox ring. So are you fine with quasi-tori? Push on the brake if not. Characteristic quasi-torus. I take a quasi-torus which has the divisor class group as its character group, or what we also can do is we look at the group algebra given by the divisor class group and form the spec of this. Then we get the quasi-torus. If you have a finally generated abelian group in our simple environment, then you can go directly to the quasi-tori by doing this, and vice versa. If you have a quasi-torus, you can directly go to finally generated abelian groups by taking the character group. It gives you contravariant equivalence. Now we are going to construct the object. We just cover our X by F and open subsets. And then we define yes. Too many U. Not too many X, but too many U. Okay. What I do is locally finite generation of the Cox ring tells me that for any finite, also as a consequence, we have for any finite open subset the algebra of sections of the Cox sheaf over UI is finally generated, so we can take the spec and obtain an affine variety. And recall, this is algebra which is graded by the divisor class group. And if I take this spec of a graded algebra, then I get an affine variety. I also already have the quasi-torus which corresponds to the divisor class group. And now it is so that this grading gives me an action of the quasi-torus on this variety. If you don't try to pretend to feel comfortable for the moment. If it gets too hard and we have time at the end, then please ask me to explain this a bit more. It acts on each of them, given by the grading. And now, if I have a group action, I look at this graded algebra, and now I want to know which functions are constant on the orbits given by x. I am looking for invariant functions. And invariant functions, one may believe... Huh? Yes. Invariant functions. This sounds very reasonable. These are precisely the guys of degree 0. Hmm? It looks as if Q-mas, was it Q-mas, I don't know, made the race, but no. No check is excluded because it doesn't make sense.
Yes.
We are, yeah. Okay, so invariant functions, one can believe, is taking sections of degree 0. If you don't feel comfortable, we can solve this problem. That is doable. But degree 0 of the Cox sheaf means what? I am looking for functions. These are controlled poles by divisors, but if there is no divisor, they must be regular. So this is just the algebra of functions on X. That is a good news, because now we can do some bricolage. This gives us, for each UI, gives us a morphism. Well, UI, the algebra of functions, is included in the algebra of functions of UI hat. Means we have a morphism in the other direction. So let us write here UI hat. We go down with this P to the UI, and maybe we take another UJ, and we go down to the UJ. What can we do below? What do we know about the intersection of two affine open subvarieties? Intersection again, an open affine subvariety. So we can not intersect the UI hats, but what we can do is put a big hat on this affine UIJ. In the sense that as we take this and then define for the U, for this intersection, define also this, and so on. And it turns out this is an open subset. And again, we can restrict our P and everything is commutative. What does this mean at the end? This means at the end that we can glue the characteristic space of X is obtained by gluing all those guys. And what we are going to glue is not only the UI head along this big head of the UI intersect uj, we can also glue the quotient map and the projection map P, because everything is commutative here. And that means at the end, everything was compatible with the grading. At the end, we get something where this H X acts on, namely on this characteristic space. And we have such we have this map. Again, this is a good quotient. For the action of H on X hat, whatever that means it has lots of good quotients, good properties. So, remark. This is a quasi-affine variety. This is a quasi-affine variety, and we have by construction what I want to relate the functions of our newly obtained X hat to what we know already. So if I take the image sheaf of this OX, the direct image, so that means you take open subsets below and associate them with the algebra of the inverse image. Yeah? And this is just the Cox sheaf. In particular, the global sections of this quasi-affine variety X hat, the global functions form the Cox ring by this construction. Ten minutes left, am I right? Yes. I mean, another toric task exercise. We had in the morning Z bar, Z hat, you remember, was the open subset of CR such that our varieties, it is exactly the same. So nothing new in the toric, after a bit of thinking, nothing new in the toric case, so we just extended it to a more general. We look at this characteristic space over X. What can we say? I mean, we can something say about X. So this is X. X is a normal variety. Normal varieties are normal, which in particular means that singularity set is not too big. So we have a big part which is smooth, So this is my X. A big part is smooth. A big open subset. What happens here? Above, I have orbits of my characteristic. So everything here, what I'm going to draw, are HX orbits. Apart from this small, what is going on here? We can find more than one orbit in the fibers. That is what good quotients allow. They are not orbit spaces, but what they do parameterize is closed orbits. They parameterize closed orbits. Somewhere are closed orbits, and others may approach these closed orbits so they are in the same fiber. So if this is the inverse image, and the good thing, and this is small, means codimension 2 or higher. The inverse image is also small. So the bed area is small below and it's small above. Which means, again, another thing, so if we restrict to the universal torso, if we cut out this up to small things, we have, but we want to keep the singularities. Because these methods also show how to deal with singularities. What else I can say in the remaining seconds? To give an impression. What is a local class group of a point in a variety, which then will be our variety? I denote it by the point X, and what I do is I don't take the divisor class group, but I mod out more. I mod out all while divisors which are principal on a neighborhood of my point X. So only Cartier, only near X. I mod out the subgroup of all D, which D is principal. Near the point X. So
how is it related with the class group of the local ring?
why defining this?
When you take the local ring,
Yes.
you take its divisor class group.
Okay, maybe it should be yeah. The point is maybe if you are going to prove things with this really turns out helpful. Maybe it's the same. I don't know. It sounds to me that it should be the same, but I never checked. So yeah. What we can say about this is that I mean, we have a projection from a divisor class group, and here we mod out a little bit more. The divisor class group projects to all of those local class groups. But that is not the interesting part. We want to relate the local class group downstairs to geometric data above. And here the proposition is the following. Oh no, even time for one more. Take a point, small x in our variety x, and what I now do is I fix a point in the fiber over this x, not an arbitrary point, as good quotient means that in each fiber, I said tell you the parameterize as a closed orbit, I find point which has a closed orbit in x hat. So then we take such a point, the orbit of which is closed in the fiber, and then also in our x. Then the local class group is the same as if I take the isotropy group of the characteristic quasi-torus action at the point x hat and take the character group of this. Okay? A corollary of this
Sorry, could you repeat the definition of Hx?
what is Hx? Hx was our characteristic quasi-torus. It acts on this characteristic space, and now I chose a point in the fiber of over. So this is a big X. I run also in this too many X's problem. I take the fiber over my point. There must be, due to good quotient, a closed orbit in the fiber. Take any out of this closed orbit. And then I take the isotropy group of the Hx action and pass to the character group of this guy, and that is the local class group. Corollary. X is Q factorial. What means Q factorial? Any divisor has a Cartier multiple. Means that all the local class groups are finite. All the local class groups finite means no, heads are missing, but at the right place. Means that all the character groups are finite. Means that all the quasi-tori, which are the spec, are also finite. So we end up with only finite isotropic groups above. So, and this means that our good quotient, which has parameterizes closed orbits, they must all be of the same dimension. But if they are all of full dimension, then there's no space for two orbits in one. Okay, so that means we have really an orbit space. This is a geometric, called geometric quotient. So we have statements, we have new statements. And by the way,
But couldn't the final not be reducible?
no,
Of those singular points?
that is, yes, irreducible, but not age irreducible.
No, they can be reduced, but they only have a unique closed orbit. So
Did you say reducible? What did you, reduced? You can have multiplicity.
Just as in your drawing. You have seen
Of course, once we have torsion, it may happen that you have more components in the fibers. That happens. But they are transitively permuted. So below it's a point. And still the orbit is still you cannot have other orbits because it's part of being the same orbit that they are transitively permuted. It looks so as each of my words makes it worse. So then maybe Klaus, I'm a bit exhausted when I'm a bit more fresh again. I promise that I take another attempt and explain it better. Again, 3 minutes too much of lecture. We haven't seen the full story. The full story begins now. Everything we prove in this framework holds as well in the toric, because toric is a special case, finally generated Cox ring. What is the next step is that I will join these two pictures. And the idea is not work for toric geometry, but benefit from toric geometry for those varieties. On Wednesday, 9 o'clock, this place. Thank you so much.